Hello everyone. Today let's solve the problem number 153. Find minimum in a rotated sorted array. So you can just go through the question. You can just go through the example as well. I'll just be explaining. I'll just summarize the question for you so that it will be easier to understand. Right. So what the question states here, we are given an sorted array of unique integers. You can clearly see here in the example they have showed. We are given a sorted array of unique integers rotated between 1 and n times. Our task is to find the minimum element in the array. In this case, we have to find the minimum element in the array using the algorithm that runs in big O of log n times. So whenever it comes to big O of log n, usually and we have to deal with the searching of an element, it's better to go with the binary search, right? So here in this case we can see here the minimum element is 1. How can we find 1? That's what we'll discuss in the approach here. See, you can clearly see here this array has been rotated thrice here. You can clearly see 1 2 3 4 5 3 4 5 thrice right here. This array has been rotated 0 1 2 5 6 7 4 times, right? 0 1 2 3 they have left 0 1 2 4 5 6 7 4 times this array is rotated, and the minimum number or the least number that is present in the array is 0. That's what we have to display. Same goes with the third example as well. 11 13 15 17. Here 11 is the least number. That's what here, right? This here it is rotated 4 times, it is rotated 3 times. They have given here, this is also rotated 4 times. This is fine. So let's see the approach first, and then let's discuss the edge cases one by one. Then let's write the code and discuss the complexity of the code that we have written. Initially, let's go with the approach as usual. So we'll be going with the approach binary search here. We just have to remember we will be going with the binary search approach. So I have considered this example just to show. So here main thing is first we have to find the mid element here. Mid element in this case is 5, right? So here if the mid element is greater than this one, the last element, then the element next to the mid element will be the least element. In this case 1, right? So the output will be 1 here. So how can we write here? If mid is greater than last element, then output will be mid plus 1, the next element to the mid. If the mid element here, if it is this one smaller than the last element here, suppose we have 1 here, in case of 5, 1 is smaller than 2, right? Then the least element will be found at the first index. So the output will be first, the element will be present at the first index. So this is the approach that we will be going with. So I hope the approach is completely clear. So next let's discuss all the edge cases and then write the code. And after writing the code, let's discuss the complexity of the code that we have written. So here let's go with the first edge case. Nothing but array is not rotated. So while I say array is not rotated, it's normal sorted array, right? So let me consider the input 1 2 3 4 5. Here first what we'll do, as usual, we'll see whether mid is lesser than or greater than this one, last element, right? So here mid is lesser than the last element. We can clearly see here. So the element present at the first index will be the least. Here the output will be 1. This is for array is not rotated. So here mid element 3 is less than 5. So the first index, the element present at the first index will be the least element. This is fine. Let's go with the second edge case. Nothing but minimum is the last element and rotation. So here let me consider the input 3 4 5 1 and 2 here. First what we'll do, this is the middle element and we'll compare middle element. Middle element is this one, greater than the last element. So the output will be, the least element will be mid plus 1, then element next to the middle element, nothing but this one, 1. So here the output will be again 1. So this is for the condition minimum is the last element in rotation. So here after 3 rotations, 1 is the smallest, right? Previously the array was already sorted, so we got 1. Here after 3 rotations, 1 is the smallest. Minimum is its last element in rotation. I hope these two edge cases are clear here. So let's move on with the third edge case. Third edge case is nothing but we are going with a single element array. While I say single element array, let me take the input 5. The output will be 5 as well, because the array has only one element, so the output will be directly 5. We don't have to compare anything, right? So what if we have the array rotated fully? While I say array rotated fully, let me consider here 1, 2, 3, 4. So here the mid element 4 by 2, we have 4 elements, right? 4 by 2 is nothing but this one. Let's compare this one. 2 is greater than 4 or not? No, 2 is lesser. So the first element, the element present at the first index will be least. This one, 1. 1 will be the output here. Because the array was sorted n times, it looks unchanged. So 1 will be the output here. So 2 lesser than 4 here. So the first element, the element present at the first index is nothing but 1 will be the output. This is for the condition array rotated fully. This one, third one was for single element array, right? This is for single element array. This is fine. These are the 4 edge cases that we have to keep in mind. So what are the edge cases that we saw here? First one was for array is not rotated. Second one is for minimum is the last element in the rotation. Third one is for single element array. Fourth one or the final one is for the array rotated fully. These are the 4 edge cases that we need to keep in mind. Now let's start writing the code, and I'll explain the code while writing the code itself, and then finally discuss the complexity of the code that we have written. So as we had discussed in the approach, we have to initialize the 2 pointers. One is left and right. Let me go with the left pointer. I'll just consider L, left, sorry, this one, let L equals 0. And let me consider the right pointer as R. I'll just point this one to the last index, nothing but the length minus 1, nums dot length minus 1. So let's perform the binary search here. So left has to be lesser than right, then only we can move forward, right? So let's calculate the middle index. In this case, mid, I'll just consider M, or let me consider mid here. So I can just consider matter floor, or let me consider the double tilde operator. So I'll just give here left plus right by 2, right? This is fine. We are just calculating the middle index. Next thing is, we already know if the middle element is greater than the rightmost element, then minimum must lie to the right of the M. Else, minimum lies at the middle or to the left of M. That's what we have to write. Let's write a simple if condition here. If nums of M, nothing but the middle element greater than the last element, then what we will do? Then the minimum must lie to the right of the M, or next element to the mid. This is nothing but L equals mid plus 1. Mid I have considered here, right? This has to be mid plus 1. Here also I have to give mid. Sorry, not M. Mid I have considered. This is fine. Mid plus 1. And else minimum lies at middle or to the left of the mid, right? I can just give here right equals mid, else right equals mid. This is it. Next, final step is when the loop ends, L points to the minimum element. Nothing but here return minimum we have considered here nums, right? Sorry, nums of left here. So here when the loop ends, L points to the minimum, this one, minimum element itself, right? So let me format the code once. Let me hit the run. So you can clearly see here the sample test cases are getting passed. So let me hit the submit button now. So you can clearly see here all the test cases are getting passed. So the code works absolutely correct or fine. So let's quickly discuss the time complexity and the space complexity here. So the approach that we went with here is binary search. We know that, and the overall time complexity would be here big O of logarithmic n, right? So why the time complexity here is big of log n? Because we are having the search, nothing but we'll only search for the one half, right? Either it might be left half or it might be right half. So we are having the search space each iteration. That is the reason overall time complexity would be big of logarithmic n. And what would be the space complexity here? The overall space complexity would be big O of 1 here. So let me consider this one big of 1. Why here the space complexity is big of 1, not the big of n? Because we are making use of the pointers, and there is no additional space required here. We are just making use of the pointers and few variables, right? Nothing, just pointers here. You can clearly see here, right? So that is the reason the overall space complexity would be big of 1 here. I hope the solution is completely clear. So for now, this is it. Thanks for watching, guys.